Hello everyone, and welcome back to my channel. So I bet most of you have seen this magnetron. However, since currently I'm in the US, I don't have any test equipment that can power this thing up. But I have tested if the filament is continuous or if the vacuum is good. So this is a functionable magnetron, which is rated at 100 kilowatt continuous output and 915 megahertz. Here I have got the datasheet of this magnetron, which you can take a look here. Yeah, it says options for 75 kilowatt, but this certain type is rated for 100 kilowatt continuous operation. Just a quick view of its parameters. Okay, so actually I have made a catalog before each of my videos. So this time I will let you see what I will talk about in this video. Okay, and sorry for this camera shaking. And I actually got the book, which is Microwave and Millimeter Wave Vacuum Electron Devices, Inductive Output Tubes, Clystrons, something more. You can search for this tube. It's a very how can I say it, instructive and interesting book. It tells you in detail like how these tubes functions and how you calculate different things for them. So let's start our topic from here. What is a magnetron? Magnetron is kind of a cross-field amplifiers. So I assume that you know what the cross-field here means. It means the electric field and the magnetic field are perpendicular with each other. So you know that assuming this red object is the cathode and the outer ring is the anode, which it says here. So whenever electron is shot out, it will move in such a curve in this cross field, right? And what is a magnetron? Okay, there's a picture of, oh yes, exactly like this one. You can see here are basically 8 small cavities like this shape. So if an electron moves in such a curve, it will induce some inductive current into this cavity, which is basically a resonant tank, because you can simply view it as many series of LC tanks. Sorry for today, I need to use this book to tell you more about this thing. Sorry for that. So basically the slot is the capacitor, basically some kind of, but the whole this shape makes an inductor actually. But what I'm saying here is that these parameters are all distributed parameters. The capacitor isn't just here. Still, they have capacitance inside this hole, right? I bet you understand that. So if you put such things, 8 cavities or some different numbers of cavities together, it should look like this. And we know that if the electron moves against the electric field, then its kinetic energy will be passed to the field itself. And in another way, if the electron is accelerated by the field, then the field gives the electric energy into this electron to increase its speed, right? So this is how basically the magnetron transforms the DC voltage into an RF power. It's functioning like when you kick off the oscillation, it works as an amplifier because like these resonant tanks and the moving electron things. So I won't talk too much about the function because I have not studied it quite well. I didn't do any calculations about this process, I would say. So let's just focus on some interesting things first. What is the cutoff voltage? So if you imagine we have a very high, very strong magnetic field, what will happen? What will happen is that the electron will not reach this anode because it will be bent like this. Like the curve has a very small radius, right? So like if we have a very low voltage, this is the same thing that we have a very strong magnetic field. So if the voltage is very low, the magnetron won't be able to work, right? Or simply if the field is too strong, the magnetic field is too strong, this thing will not function as you design it. So what is the cathode heating? Okay, the cathode, you know, in a vacuum tube is the source of the electrons. So for this tube here, the cathode connection is, I assume, yes, it's this ring here and this ring here. You can see that there is a ceramic insulator here which hold the vacuum. And between these two pins, you apply the filament voltage, which is this volt here, and this current consumption over like maybe 1.5 kilowatt or something, maybe, yeah. So this is a cathode for providing the free electrons. But something interesting will happen here, different than in other electron tubes, is that even it's functioning correctly with the suitable field strength, some electrons will still be returned to the cathode with a high kinetic energy. This part of electrons is roughly like 10% of the total electrons, which form the electric current from the anode to the anode to the cathode. So the heating effect of the cathode will be very significant in comparison between like magnetrons and other electron tubes. So some tubes, they even operate like this. They have an integrated small part in the cathode, which is a high emission rate. I would say it's a high emission rate thing inside it. When the magnetron starts, it will first power up that small region to provide the electron source. Once the electron hits back to the cathode, it still keeps heating the cathode hotter and hotter. Once the whole cathode reaches its operation temperature, they even can reduce the voltage of the cathode or completely cut off the cathode power supply. Actually, in most of the radar magnetrons, this will say something about like you should decrease the cathode heating power, with respect to the anode voltage, which is actually the output power of the magnetron. Okay, so we finished talking about the cathode heating, and okay, what is the tuning of a radar magnetron? Yeah, mostly radar uses the pulsed magnetrons, which you can see like this one. This one, I assume it's a World War II version, maybe. I'm not sure, but yeah. So radars, they use pulsed magnetrons because they need to receive the reflected microwave to determine something, right? So in modern radars, they have kind of a variable frequency thing, but I'm not sure like why they need that. But I will basically talk about how we achieve a variable frequency magnetron. So this thing is not variable frequency. This one is not. But if you remember what we talked about, what determines the frequency is that the LC parameter here. inside these cavities. So if we change the L or C parameter during its operation, then we are changing the operation frequency. So how can we do that? There are two basic things you can change: the capacitance or the inductance. So for changing the capacitance, sometimes they will put, I will call it, insert a small pin into each of these slots or something. They will insert and pull out a pin into this, so it can change the distance between the two plates of the capacitor. Or they place a ring above this plane. You can imagine that they place a ring here, and the ring will couple a different side of these small capacitors. Okay, but basically it's the same function as insert or pull out a pin here. So what is the inductive changing the inductance? That is, place a closed loop into these things. You can insert a pin into these openings, big openings. Metal pin is basically like infinite amount of closed rings, right? That's how they change the frequency of such things. But that way is kind of a mechanical moving and out. It won't be able to do it at a very high frequency. But how to do it with a higher frequency, with a purely mechanical way, is that they have kind of a plate, rotating plate, like above this plane here. On that plate, they have cut out many holes which can coincide with these different holes. When it's spinning, it will coincide with these holes, and it will be some holes being missed and coincide again. You understand that? So it's basically still changing the inductance, right? Because it's symmetric when it's rotating. I'm not sure if the capacitance changes, but basically like that. So this is the tuning of the radar magnetron, and why impedance matching is important in a magnetron. In most of the RF, in all of the RF circuits, I bet that impedance matching is an important thing. But how will it influence the magnetron? I will not talk too much about the frequency drag or something. I will simply talk about how will it destroy a magnetron. Okay, if you look closely at this magnetron, where is it? Antenna. Where is it? Okay, it's inside this ceramic protection cover, I would say, like dome or something. This is some ceramic, same material as this and that one, and there's an antenna inside, but that antenna is not what you think, it's a emitter or something. It's kind of a central conductor of a coaxial cable, because this whole thing will be inserted into a cavity. Without the cavity, it can work, but the impedance matching is terrible. This thing is just a protection. It's not the antenna, what you are seeing here. Inside there is an insulated metal bar inside, which is insulated from the outside. And that thing that actually functions as a central conductor of the coaxial cable. So maybe you are assuming that, if we have a bad impedance matching, maybe plasma will be generated on that antenna. True, that's for sure, because you can see many microwave plasma videos. Even I have tried that with ordinary oven magnetron. But that's not the major damage which will happen, or I would say that's not the that if that thing happens, before that happens, something inside already happens. So what is really happening is that if you have a bad impedance matching, You remember these things are resonant cavities or resonant tanks. They have high voltage across the capacitors for sure. So if you have a bad impedance matching, the voltage across this blade, I'll just call it like that, the voltage across it could be very high, and discharge could happen there. Once you have the discharge, some of the material will be vaporized and condensed into some previously insulated area inside this magnetron. Since it's vacuum inside, it's very easy for the metal to evaporate. So that's basically what will happen if you have a bad impedance matching in high power magnetrons. Okay, so power adjustment. Okay, let's find a proper picture of it. I'm not sure if this. Okay, let's just do it. I would say that how could we? Oh, by the way, how is the antenna connected with these cavities? How we get the energy out? So since this is an inductor, we can use kind of a transformer way. This is exactly what this thing here does. You see a not closed loop, and the alternating RFB field, like the RF magnetic field, is perpendicular to my screen, right? Goes in and out, so it will induce a RF current inside the antenna. And most of the industrial heating magnetron, like this one, I believe they have 10 cavities inside, and they have 3 of these not closed loop thing, and it will be parallel together at the ending and connected to the coaxial thing I was talking about. So power adjustment. Okay, so if I want to adjust the power, then I need to adjust the anode voltage, and accordingly this anode current will change for sure. But you remember that this voltage should be adjusted with respect with the magnetic field, right? So if you want to adjust its power, then the B field must be adjusted. Basically, these two things, like the B field and the E field, are roughly proportional to each other. So if you decrease the voltage by half, then you decrease the B field by half roughly. And yeah, I saw that they over magnetron, they use a stronger magnetic field and a higher anode voltage to accomplish a higher operation power. This is power adjustment. And why industrial magnetrons use electric magnets? Okay, so if you have ever tore down an oven magnetron, I bet most of you who is still watching this video till now must have done that. You will notice that though this shape is just like magnified oven magnetron thing, it is very clear it lost something. Yeah, you are correct. You didn't find any magnets on it. How we achieve the B field? Okay, we basically use an electric magnet to accomplish this task. Why we do that is that actually this electric magnet, part of its current will be from the anode current to accomplish kind of a feedback and to stabilize the operation of this magnetron. So for last thing I will talk about is that this magnetron actually uses a pure tungsten metal cathode. It has 0.3 to 0.7 ampere per centimeter squared. Like the electron density or electron emitting rate at the working temperature of the cathode, and it has 1 per watt filament heating power will give you 4 to 8 milliampere cathode maximum available current. So these two hoses here are for the water cooling. And let's see if there's anything more I can talk about. I don't think so, but yeah, that's where the vacuum is drawn. And yeah, that's basically all of this magnetron. And if you have any questions, you can ask me. Yeah, thanks for watching and have a good day.